All right, so let's go over this one, and then we'll do the last one from the worksheet. This one says sketch. The function's name is what? G. Yeah, g of x or g. And it's a piecewise function. You can spot it pretty quickly. How do you know it's a piecewise function? Yeah, it's called the brace. Kind of looks like a Jay Leno profile, if you will. Kind of a big old chin, a pointy nose, and kind of a little pompadour there. So with an open brace, it's a piecewise function. And if you look at the individual pieces, it's part parabola here. That's an x squared function. It's part reciprocal function, 1 over x. And it's part line, 2x minus 1. So everywhere to the left of -2, it's the quadratic. And then it switches at -2, you can see here, to 1 over x. So remember, the way you read a compound inequality is from the inside out. You say that x is greater than or equal to -2 and less than 1. And then at 1, it switches to the line and becomes the line forevermore. Now, the parent function 1 over x, let's kind of go over that. It's one that you're responsible for. Let's actually do all of them here. Y equals x squared, y equals x, and y equals 1 over x. Okay, the parent functions, you had these in algebra 2. X squared is the one that bounces on the origin, and it looks like that. Okay, y equals x, that's the parent function for all lines. It looks like that. Also passes through the origin, has a positive slope of 1. And then 1 over x is the reciprocal function. It has a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. The reciprocal of a positive number is a positive number, and the reciprocal of a negative number is a negative number. So this guy lives in quadrants 1 and 3. Okay, and the idea being that if x is a small number, like 1/2, the reciprocal of 1/2 is a big number too. Or if x were a really small number, like 1 over 100, the reciprocal of 1 over 100 is 100. And as you go out to the right, like to 100, the reciprocal of 100 is 1 over 100. So that's why there's asymptotes on both sides. There's another parent function that I might throw in there. It's a radical function. So let's review him real quickly. Kind of do it the same way. The radical function is the square root of x, and that's the one that's the parabola that's reflected across the line y equals x. But to be a function, we only look at the top part of it. So it looks like that. It's basically the parabola turned sideways, if you will, but we don't look at the bottom piece. All right, so this piece is part of the 3 parent functions at the top. The most important thing when you're sketching a piecewise function is to draw the graph large enough so that you can have room to make your transitions. The most important x values are the ones where it's changing from one function to another. So that's at -2. And I'm just going to come over here and call that -2. And then at +1, which should be a little bit closer to the y-axis on the right side than -2 is on the left side. All right. Now that you have that, the next most important step is to determine the y values where one graph stops and the other one begins. We're only letting it be the parabola x plus 2 squared to the left of -2. Now, think about transformations. When you add a 2 to the equation of any function, whether it's a parabola or a line, what does that do to the graphs transformation-wise? Well, because it's inside with the x before we're squaring it, it's going to affect the graph's x values, which means it's a horizontal change. Okay, if that were like x squared plus 2, now you're affecting the y values. It moves up 2. But it's on the inside, so x plus 2 is actually going to shift it left or right? Left. It's the opposite of what it immediately appears. So it looks like plus 2 is going to be to the right 2, but it's actually left 2. So the old vertex, which used to be right here at the origin, okay, we're picking this blue graph up and we're moving it left 1, left 2 units. So it's actually going to be bouncing now on the origin. But here's how you can determine the y value. Even though it's strictly less than, not less than or equal to, if you plug that -2 in up here to the top piece, what do you get? -2 plus 2 is 0. 0 squared is 0. That's how you determine the y values. Now, because it's strictly less than, you're going to put a what there? Open circle or solid dot? Open circle, okay? So there's an open circle at -2, 0. And now knowing what the graph looks like, it comes in, boom, right there. And if that were to continue, it would start going up immediately on the other side of -2. All right, so you're graphing these piece by piece, and you can only graph them on the interval where it's defined. All right, the next piece, 1 over x, we know it looks kind of like this, but we're only sketching it from -2 to +1. So again, we want to know the y value where this graph picks up at and the y value where he ends at. So to determine the y value it starts at, plug in your -2. What do you get when you plug in a -2? -1/2. Good. So -1/2 is going to be about right there. I'm just going to label it as -1/2. And I'm going to move my -2 label up above here so it doesn't interfere. Do I put a solid dot or an open circle there? It's x is greater than or equal to, so a solid dot. So at -2, -1/2, I'm putting a solid dot right there. All right, now let's go ahead and figure out where it ends. It's going to be from -2 all the way up to 1, not including 1, but I can still plug a 1 in. 1 over 1 is 1. So that's going to go over here to 1, 1. And is it a solid dot or an open circle? Open circle. Yeah, because it's strictly less than. Now all I got to do is between -2 and 1, I just draw this graph right there. Okay, so I need to know what it looks like. Well, here we go. I know that from there it would go down, and there would be a vertical asymptote right there on the y-axis. And then I know from what I just did, let me move this down a little bit. Okay, then I know it's going to have a vertical asymptote here. Oops. And so it's going to come from that vertical asymptote and go right up to that open circle. And we typically draw lines on the end of our graph or at a vertical asymptote. All right, so notice that if you were to imagine this graph that I just drew a piece of, if you were to imagine it continue going in both directions, it would look very much like this right here. We just only drew it. If you want to trace this one out, we drew it from here to here. We only drew that much of it, okay? Now we got that taken care of. It says when x is greater than 1, it's going to be the line. Well, how do I figure out the y value where it starts? You simply plug it in. 2 times 1 is 2. 2 minus 1 is 1. So this is kind of nice. It actually starts at the exact same y value that 1 over x ends at. But is it solid or open? It's also open because it just says x is greater than 1. So how do you draw a line with the slope of 2? Well, as long as you think of like a slope of 1 as being your 45-degree slope, right? So as long as you come out of here and draw it with a slightly steeper slope than 1, you're in good shape. And there you go. That's what the graph of this function looks like. Does it pass the vertical line test? If you drew it correctly, it should. Because the way it's defined, there's no overlapping x intervals. So it's kind of like a 3-for-1 deal. You're sketching 3 separate functions all on one graph, okay? So once you get the x values identified, the most important thing after that is to determine the y values where one ends and where the other one begins. And it's just a matter of putting solid dots or open circles there. All right, let's go ahead and talk about it a little bit then. What would be the domain of this function? And right now, graphing it is probably the easiest way to determine the domain. For what values of x do we actually have an output? Well, the pieces themselves, the ones on the ends at least, were continuous everywhere. So do we have a y value at -2? Yeah. What about at 0? No. The piece 1 over x had a built-in vertical asymptote at x equals 0. So we'll go ahead and say it's a set of all x such that x is not equal to 0. The next piece that was in question was at x equals 1. Do we have a function value at 1? We actually don't. And it was because the function itself was explicitly defined to only be left of 1 and at 1. And so in this case, 1 is also not in the domain. And those are the only two. Now, I could have easily added another piece. If I take this piece here and kind of move it down a little bit, if I would have said let it equal 2 when x equals 1, then I would come up here at 2 and I would put a solid dot right there. And now I would actually have just 0 not being in the domain. But I didn't do that, okay? I didn't do that. So let's go ahead now and talk about the types of discontinuities. We have 2 values that are not in the domain, but how many discontinuities do we have? We have 3. Okay, let's go from left to right. The first break in the graph is at -2. What type of discontinuity is that? That's a jump. So we'll say G has a ... a jump at x equals -2. So the jump discontinuity is always going to happen in this case. If you think of the graph itself as being roads, and if you think of the dots themselves as being like the bridge that connects two roads, or a manhole cover that connects two roads, whenever the roads are coming in from either side to different y values, this one's coming in from the left and approaching 0, this one's coming in from the right approaching -1/2. Whenever your two y values are approaching different y values, you have a jump, okay? And remember, we just say at x equals. All right, the next one is where? Where's the next discontinuity going from left to right? The vertical asymptote. So x has a VA, you can write that at x equals 0. Now you can always plot a vertical asymptote from the graph, because even without the dotted line, because from the left side or the right side, it's going to be forcing your values down to -infinity or positive infinity. That's why we call it an infinite discontinuity. It forces the y values up or down. And then the last one, at x equals 1, we have a what? A hole at x equals 1, or can we do better than that? Very good. The hole is known as the point discontinuity. So now we're always going to have to list it as an ordered pair. And the ordered pair where the hole is at 1, 1. Now what if I did leave that in there? When x is 1, call it a 2. If I went back and did that, would that change the type of discontinuity it is? Is it now a jump? Nope, it's still a hole. The jump only happens when the two roads from either side are going to two different y values. This is still a hole. The road from the left is going to 1. The road from the right is going to 1. This is still a hole, okay? Would the hole still be at the point 1, 1, or would we say now it's at 1, 2? Nope, the hole is still at 1, 1. So for the removable point discontinuity, we don't care if the dot is above the hole or below the hole or doesn't even exist at all. It could be completely gone. The only place it can't be is plugging the hole, because then it's not a discontinuity. All right? So you will have a hole every single time your road from the left, bless you, and the road from the right are connected by an open circle. Every time that's a hole, regardless of where the little manhole cover is, okay? And it's always going to be at the y value of the hole. So that should clear some things up. Here's a perfect one that has one of each of the three types that you're responsible for. Okay, any questions on this one? Let's go then to the worksheet that y'all just turned in. And I know there was a fantastic one on there. It was the last one. This is the one that a lot of people had a question on. Let's actually do something else first. Let's take a look at G and H. Kind of comparing. Well, that's not the one I wanted. Which one did I want? I wanted these. E and F. E and F. Let's compare and contrast. So here's another way to define a non-overlapping interval. Instead of saying less than, right than, you could say x is not equal to. That means on either side of 3, the graph is going to look like, in this case, x squared. So to sketch this function, let's go ahead and give ourselves an x and a y axis. And 3 is the most important value, so I'm going to go ahead and put the 3 down. Now I'll pick a flavor for the graph. How about purple? We know then that when this graph gets to x equals 3, the x squared function is going to be what? What do you get when you plug in the 3 into x squared? 9. So I'm going to go ahead and put 9. Would I put an open circle there or a solid dot based upon the top definition? Open circle, it says when x is not 3. That means to the left of 3 and to the right of 3, it's defined by x squared. So I'm putting an open circle there. And now all I got to do is draw my x squared graph. Well, x squared has y-axis symmetry. So that's why you want to do it like this. You should be able to fold that graph on the y-axis and have it line up with itself on either side, except for the hole. And by the way, that is a hole, right? We have a hole at the ordered pair 3, 9. Someone came to the perfectly beautiful x squared graph and swiped away that ordered pair 3, 9. Now, I'm going to go ahead and lasso this with scissors and copy it. Now I go to the next piece, and it says, hey, when x is 3, at that exact value of x, what are we defining the y value to be? 9. So guess what it does? It plugs the hole. And now we have the graph. Do we actually have a hole at 3, 9 anymore? No. So you could think of this piecewise function as having the same phenotype as the graph of x squared. Phenotype meaning physical appearance. Okay? The graph of x squared and this purple graph here that's f of x, they look exactly the same. But they have a different genotype, don't they? Genotype is genetic code. F of x has like an x squared, but it was not equal to that at 3. But then it was explicitly defined to be 9 at x equals 3. So you can think of this one as having like maybe some kind of birth defect, like a hole in its graph somewhere. And then as mathematical surgeons, we went in and found the y value of the hole, and then we fixed the hole. We plugged the hole. Okay? Different genetic DNA, x squared and this piecewise function, but the exact same phenotype. Now, if you come over here to f, notice the first part is the same. Let it be x squared to the left of 3 and to the right of 3. That's what not equal to 3 means. So if you want to paste that in there, that's going to be the same first part. But now it says when x is equal to 3, we're going to call it what? Negative 9. So now the dot's down there. If the attempt was to plug the hole, we're bad surgeons at this point. We missed it, okay? But that's not really the point. The point is that these could be anything. You just have to look explicitly at how it's being defined. Do we have a hole now? Yeah, now we have a hole on the graph of f at the point 3 comma what? 9 or negative 9? The hole is at 3 comma 9. What is f of 3 though? Negative 9. Very good. The hole is at 3 comma 9 because that's where if you had a manhole cover, you could put it right there and make the graph continuous again. That's what the previous graph did. But the function value is f of 3, and it's always looking, where's the dot? Where's the function actually defined there? What's the domain of this function? All real numbers. Very good. All real numbers. So there you go. Piecewise functions. Pretty darn important. 2 for 1s, 3 for 1s, whatever. Let's look at the last one on here. It was a 3 for 1. All right, so we're going to start off this time with the reciprocal function everywhere to the left of positive 1. So let's go ahead and give ourselves an x and y axis. Y axis, x axis. And what's the most important x value on this entire graph? 1. So I'm going to come over here and just arbitrarily call that 1. Now, everywhere strictly to the left of 1, it's going to look like 1 over x. So we know what that's going to look like. We are still going to see the vertical asymptote at 0. When you plug in a 0 to 1 over x, you get 1 over 0. That's non-zero over 0. That means a vertical asymptote. And we are still going to see the horizontal asymptote. I'll go ahead and extend it both ways. So we're going to go ahead and draw that graph to the left of 1. So to the left of 0, we see the entire thing this time. So that's what asymptotes do. It's going to kind of come from the negative side of 0 and kind of gently pull away. And as it gets closer and closer to the vertical asymptote, it's going to be tugged away by the vertical asymptote. They act like gravitational black holes. The graph is irresistibly pulled towards them. But now on the right, when I come from positive infinity coming down, as I make my turn, instead of continuing on, I'm just going to get to that vertical position and put an open circle. Why an open circle? Strictly less than. Now here's the deal. I need to know what that y value is where it stopped. How do I figure that out? Plug it in. Even though it's less than, we'll plug in the 1. 1 over 1 is 1. So I know it stopped at the point 1, 1. I just put an open circle there because it wasn't equal to. All right, so far so good. Now we'll do this. I'm not sure exactly yet what this one looks like, but I do know that I can figure out the y value it starts at by direct substitution. And whatever y value it is, because it's strictly greater than, I'll put an open circle. That'll give me at least a place to start. So what do you get when you plug a 1 into that whole second piece? You get a -2 in the top and a -10 in the bottom, right? Well, that simplifies to 1/5. So there is going to be an open circle again at 1, 1/5. Now I'm going to call 1/5 right there, just a little bit below that other open circle. And notice those open circles now are directly on top of each other. Okay, they're stacked vertically at x equals 1. Now how are we going to figure out what that graph looks like to the right of 1? Well, let's come off to the side and do a little bit of independent analysis. If this were x minus 3 over x squared plus x minus 12. If I just asked you to tell me something about that function by itself, you would probably notice that it's going to have some domain restrictions, right? So we've been practicing in isolation. There's a quadratic. So we know then that x squared plus x minus 12 cannot equal 0, and it could have up to 2 discontinuities. Well, how are we going to solve that? We factor it. X plus 4, x minus 3 can equal 0. So for that independent function, I know that x can equal -4 and x cannot equal +3. That would be the domain of that function. But that's only a piece of the function. We're only looking at that function to the right. That's what greater than means, right of 1. So are we going to see any of those discontinuities? In other words, is -4 or 3 to the right of 1? Only one of them is, right? -4 is not to the right of 1, but 3 is. So if we were to factor this completely, it would be x minus 3 all over x minus 3 times x plus 4. What type of discontinuity do we have at 3? There's a hole. This function would have a hole at 3, comma, and you remember how to find the y value of the hole? Put a 1 there. Now, when you divide out something in the top, like x minus 3, make sure you put parentheses around it. I've said that before. So that when you divide it out, we know you're taking the whole thing. And it's always a good idea, if there's nothing left in the top, to just put a 1 so that you see something there. Now to find the y value of the whole, remember, we plug this 3 right back into whatever's left. So you get 1 over what? 7. So that function by itself has a hole at 3, 1/7. We know we're going to see that hole because 3 is to the right of 1. So I'm going to come over here and just put 1/7, which is a little bit less than 1/5. And if that was 1, this would be 2. 3 would be somewhere right around there. I'm going to put an open circle there. And notice it's a little bit lower than those two. Now I kind of know what this graph is going to do. I have points essentially that I can connect. Now they're not really points, but they're open circles, so they're kind of acting like that. And it's going to approach 0 from above. Because remember, what is left when you divide it out? You get the graph of 1 over x plus 4. And 1 over x plus 4 is the graph of your 1 over x function that is shifted what 4 units? Left 4. Good. This one would have a vertical asymptote at -4. We're not seeing that vertical asymptote because -4 is not greater than 1. So it would still approach 0. And there's what your graph looks like. Inch by inch, it's a cinch, right? Piece by piece, it's pretty easy. Let's go ahead and figure out the domain now. This function's name is f for freaking awesome. The domain of f is the set of all x such that x is not equal to what? Let's go from left to right. What's the first value that's not in the domain? 0. Good. That's the built-in vertical asymptote to the 1 over x piece. Comma. Where's the next x value that's not in the domain? 1. Good. And that was explicitly defined. Again, less than 1, greater than 1. And then the next discontinuity at 3. So in this case, every value that is not in the domain is also a discontinuity. In the previous one that I saw, or 3 ago, the one we warmed up with, one of the discontinuities was in the domain. Let's go ahead and name the discontinuities now. F has a ... from left to right, a VA at x equals 0. What type of discontinuity is there at 1? That's a jump, because the roads, if you think of the graph as the roads are going to 2 different y values. From the left, it's approaching 1. From the right, it's approaching 1/5. So we have a jump at x equals 1. And then what type of discontinuity do we have at 3? That's a hole. So we have a hole at 3 comma what? 1/7. Excellent. Now what if I did come back into the piecewise function and said let f of 3 equal 1? Because I could easily do that. Would that still be a hole at 3? Yes, it would still be a hole at 3, but now 3 would be in the domain, so we would actually take it away. But in this case, it's not. It's kind of talking about what ifs. So if you understand that one now, you're in good shape. Your parent functions are x, x squared, 1 over x, and the square root of x right now. Okay, and as we need to work with more, I'll introduce you to more. You should have seen all of those at least once or twice in Algebra 2. All right, any questions on piecewise functions? Let's give you all one to try on your own, okay? So you can add this to your notes. Let's let this one be m of x, or Monday of x. M of x equals, let's do 2x minus 1 when x is less than or equal to negative 1. Let's let it be x squared minus 1 from negative 1 to 0. And then let's let it be the square root. Or actually, let's do this. Let's let it be equal to 3 when x is 0. And then let's let it be the square root of x when x is greater than 0. So this is a 4-headed little kitty cat. Okay? Kind of cute, but still creepy. Yeah. Go ahead and sketch that one based on what we just did. Piece by piece, inch by inch. It's a cinch. And I'm not going to stop the video here, so if you're watching the screencast, you're trying it at home. Leave it running. Bless you. When you're making your graph, you don't have to put like negative 1 like immediately to the left of the y-axis. If you look at the x values in the beginning, we're only switching at negative 1 and 0. Kind of stretch out the x-axis a little bit so you give yourself some space to sketch things horizontally. The x and y-axis don't even need to be the same scale. As long as when you label it, you kind of preserve that scale on each independent axis. Put your x values down, and then, of course, where does one y value end, and where does the next y value begin? Open circles versus solid dots. You will be sketching a piecewise function tomorrow on your quiz. Maybe not 4 pieces like this one. Yeah, I think the x squared minus 1, that second piece, it's going to be coming up to negative 1 on the y-axis. Right. That's from the left. See, from the left of negative 1, it's supposed to be the line. You have it from the left of negative 1 being the parabola. A piecewise function is kind of like a small little computer program, really. The numbers or the values of x on the right are kind of like your inputs, like if-then statements. If x is less than negative 1, then graph 2x minus 1. If x is between negative 1 and 0, then sketch the parabola x squared minus 1. If x is 0, then put a dot at 0, 3. And if x is bigger than 0, sketch the function square root of x. Okay? So even though we put them second, they're kind of the first things we consider. Some of y'all are still struggling with that, so let's go through it. Okay, so I already did my x and y axis, and I already realized that based upon the definitions of the x's, negative 1 is going to be a place where it changes from a line to a parabola. 0 is going to be a place where it changes from the parabola to a radical function. So here we go. I am first and foremost going to do the following. I'm going to plug a negative 1 into there to see where that y value is when that graph stops. Okay? Because we're graphing that everywhere to the left of negative 1. When you plug in a negative 1 there, you get negative 3. So at negative 1, negative 3, because it's going to be equal to, I'm putting a solid dot. So negative 1, negative 2, negative 3. So that looks good right there. So at negative 1, negative 3, there's a solid dot. Now I got to sketch it as the line 2x minus 1 everywhere to the left. So what do you know about a line with the 2x minus 1? The slope is what? 2. So it's just going to come in with the slope of 2 from negative infinity. Of course, you don't have to draw it all the way at negative infinity. Your iPad's not that big. So just have it coming in like this. All right. That has a positive slope because it goes up from left to right. All right. So far, so good. Now, I want to figure out where the parabola at negative 1 starts. So by direct substitution, I'll plug this negative 1 in here. What's negative 1 squared? 1 minus 1 is 0. So at negative 1, 0, because it's now x is strictly greater than negative 1, I'm putting an open circle at negative 1, 0. And I'm going to go ahead and find the right endpoint too, because it's easier if you have your open circles or solid dots first because they become guidelines. Now it says when x is less than 0. So at 0 is where it ends. If you plug in a 0, 0 squared minus 1 is negative 1. So I'm putting another open circle there at negative 1. And now all I have to do is draw a little piece of a parabola there. Well, the parabola, x squared minus 1, would be your just regular old parabola that opens up, and the minus 1 now scoots it down 1. So negative 1 is going to be the y-coordinate of the vertex. So it's going to look like this, just something that curves. And if you were to continue it to the right, it would look like that. That's what your parabola would look like if you continued sketching it. But we're not going to do that. So I'm just going to get rid of those lines right there and get rid of those lines right there. Okay. Then it says, hey, when x is 0, call it a 3. 1, 2, 3. So now I'm just going to put a solid dot right there. When x is 0, call it a 3. And then finally, when x is greater than 0, which means to the right of 0, call it the square root of x. Well, again, I want to know the y value where this one picks up. So if you plug in a 0, you get the square root of 0, which is 0. That's the origin, 0, 0. Do I put a solid dot or an open circle? Open circle. So an open circle at the origin. And now it looks just like the graph of the square root of x, so it looks like that. And there is your piecewise graph. Yay. Inch by inch and piece by piece, it's easy to do. Easy to do. Let's go ahead and find the domain of m of x. It's easy to get the domains from the graph. Once you have it, we really should be able to get the domain eventually from the equation. But let's look at the graph. The first discontinuity is negative 1. Is negative 1 in the domain, though? Yeah, the y value is down there. So it's a discontinuity, but it's still going to be in the domain. 0 is the next discontinuity, but is 0 in the domain? Yeah, it has a function value up there at 3. So what's the domain of this function? All real numbers. There's no built-in discontinuities. The pieces themselves did not have any discontinuities. All right, now let's name the discontinuities. M has a ... The first discontinuity is at -1. What type is it? A jump. Okay? We list that as just the x value. At x equals -1. Okay? Again, the jump is when the roads don't line up. The road from the left is approaching -3. The road from the right is approaching 0. You physically have to jump from one road to the next road, just like Bo and Luke Duke would have to do on the Dukes of Hazzard. Okay? The next discontinuity is at 0. What type of discontinuity do we have there? Also a jump. Yeah. At x equals 0. So this one had 2 jumps. Notice the function value here is not plugging one of the holes on the end of the jump, which is fine. It doesn't have to. That's irrespective of the fact that it's a jump. Okay, any questions on that? All right, well, I think that's it for piecewise functions. We have 8 minutes left, so I think I'm going to start 2.1.